AB Calculus, section 3.11 on related rates. Our goals today in this video are to set up and solve related rates. Prior to doing so, what I would like to look at is using implicit differentiation to work with a function that has multiple variables. For example, the area of a circle is equal to pi r squared. If I wanted to differentiate, though, with respect to a third variable, let's call that variable t, and let's consider t equal to time. I would take the derivative of both sides with respect to t, and so now both a and r have an unknown relationship with t. So we are going to be implicitly differentiating both sides. Therefore, dA dt, which would be the change in area with respect to time, would be equal to 2 pi r times dr dt, which is the change in the radius of the circle with respect to time. So now these are called related rates because they're related to each other. When we bring in a third variable, the area and the radius clearly are related to each other based on the formula to start with. But when you throw that third variable in, now their rates of change are also related. So let's look at example number 1. An oil rig springs a leak in column C's and the oil spreads in a circular patch around the rig. So circular patch tells me area pi r squared. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the radius is 100 meters? So what we want to find, okay, typically you have a find, a given, and a when. What we want to find is how fast is the area changing or increasing. So we want to find dA dt. That's the value we're seeking. We are given that dr dt is equal to 30 meters per hour. And we want to know what dA dt is when r equals 100 meters. Okay, so let's work from the very beginning. A is equal to pi r squared. So dA dt, as we did above, is equal to 2 pi r times dr dt. All right, now as we work through this, we've got some values we know, and we've got some values that we're seeking. Clearly, we're seeking dA dt based on the information above. We are given r is 100, and dr dt is 30. Therefore, dA dt, make sure and pay attention to units, will be, oh boy, what is that? 30 times 100 is 3,000 times 2 is 6,000 pi, and now in units for area would be meters squared per hour. Okay, there you go. That's your first related rate problem. Let's do another and see if we can clean up maybe some of the gaps. All right, here we are, example 2. An observer stands 200 meters from the launch site of a hot air balloon. The balloon rises vertically at a rate of 4 meters per second. How fast is the angle of elevation of the balloon increasing 30 seconds after launch? Okay, so what we want to find is d theta dt. That's the change in the angle with respect to time. Okay, we are given that the balloon is rising vertically at a rate of 4 meters per second. That tells me dy dt is equal to 4. Okay, and this happens when 30 seconds after launch. Okay, so if the balloon starts at the ground, 30 seconds after launch would be 30 times 4, right? So 4 meters per second for 30 seconds. I think that's 120 meters. So we want to know that when y of 30 equals 120. Okay, so let's bring these variables together. So in the previous example, we could combine area and radius using the equation of a circle. How would I combine this? How do I connect theta with y and 200? Well, the tangent of theta is equal to y of t over 200. Okay, so now we've related those two values. All right, let's take the derivative of both sides with respect to t. So that would be secant squared theta times d theta dt will equal 1 over 200 times dy dt. Okay, so what we know, all right, what we know here, and I'm actually going to draw the triangle, is that at 30 seconds after launch, we have 200, we have 120. So using the Pythagorean theorem, I'm going to get that the hypotenuse here is 54,000, square root of 54,400. Okay, so why do I need that? Well, because I need to find the secant squared of theta. Okay, so my ultimate goal is clearly to find d theta dt, but I need to plug some values in. Okay, so that's why I need to utilize this value for the hypotenuse. So the cosine of theta is 200 over the square root of 54,400. So the secant of theta would equal the reciprocal of that, 54,400 over 200, but the secant squared would be that squared, which comes out to be, using my calculator, 1.36. Okay, so I've got 1.36 times d theta dt is equal to 1 over 200 times dy dt, which is 4. Okay, so I can simply isolate d theta dt, which will equal, this would be 1 over 50, right, if I reduce 4 over 200, divided by or times 1 over 1.36. All right, now when you get d theta dt, your answer, first of all, your calculator should always be in radian mode, but your answer will always come in up in radians as well. So this would be radians per whatever the unit of time is. I think it's seconds. Okay, so use your calculator and take 1 over 50 and divide it by 1.36, and we get 0.01 to 3 decimal places that would become 0.015 radians per second. So that is the rate at which the angle is increasing as all of the other properties of this problem are continuing to move over time. Okay, let's look at a third example. Okay, sand falls from an overhead bin accumulating in a conical pile. Okay, so cone, notice I've given you the formula. We will give you the formulas for these geometric areas and volumes for the most part, unless I believe it's the area of a circle. Then I believe we kind of hold strong to the fact that you should know that. Okay, so the sand falls from an overhead bin accumulating in a conical pile with a radius that is always 3 times its height. So radius is equal to 3 height. Write that down on the side. If the sand falls from the bin at a rate of 120 cubic feet per minute, that's given. That's going to be dV dt. All right, and you can tell it's volume because it's feet cubed. So that's 120 cubic feet per minute. Okay, how fast is the height of the pile changing? So that's dH dt. We don't know it. When the pile is 10 feet high, so h equals 10. Okay, so let's look at volume quick. Volume of a cone is 1/3 pi r squared times h. Now r is kind of irrelevant within the context of what we want to find, what we're given, and when. So I want to sub in, for r, I want to sub in 3h. So I want to make volume in terms of height only. All right, so that'd be pi, 1/3 pi. R is now going to be 3h, and that'll be squared. Okay, so volume with respect to h only, where r is now irrelevant, will be 1/3 of pi times 9h squared times h. So we can simplify yet again. The 9 and the 1/3 will reduce to 3. This will be pi h cubed. Okay, so that's volume with respect to height. And that's all we need now when we differentiate with respect to t. So differentiating both sides with respect to t, I get dv dt is equal to, now I use the power rule, that'll be 9 pi h squared times dh dt, utilizing my implicit skills. Okay, now we use what we're given and when it happens. So dv dt is 120. This will be 9 pi times h squared times dh dt, which of course is what we're trying to find. So that will equal, it looks like 120 divided by 900 pi will equal dh dt. Let's clean that up just a little bit and give it units. So dh dt will equal, oh boy, let's do this. Let's drop the zeros. I believe 2 goes into both, so that'll be 6, that'll be 45. And then 3 goes into both of those, so that'll be a 2, and that'll be a 15. Okay, so I get 2 over 15 pi, and units here, since its height, will be feet per minute. All right, there you go. You could leave that as a decimal answer, totally fine, but dh dt will be that rate. Okay, let's look at another example. Example number 4, assuming that a soap bubble retains a spherical shape. Okay, notice I've got the volume of a sphere formula given to you. As it expands, how fast is the radius increasing? Okay, so dr dt. When the radius is 2 inches, r equals 2 inches, if air is blown into it at 4 cubic inches per second, so dv dt is 4 inches cubed per second. Okay, so volume, as we know, 4/3 pi r cubed. Differentiating both sides with respect to t gives us, the 3 comes down, makes the 4/3 a 4. That'll be pi r squared times dr dt. Okay, let's sub in and find dr dt. So dv dt is 4. We got a 4 times pi times the radius squared, which was 2, times dr dt. Therefore, I'm going to get 4 equals 16 pi times dr dt. And therefore we get, I believe that'll be 1 over 4 pi. And that'll be, since we're talking radius, inches per second is dr dt. Okay, you guys, as you get going on this, you want to find a way to relate the variables. And most of the time we give you the way that the variables relate. However, on the previous problem where we talked about how r and h related, where the radius was always 3 times the height, that's one of those situations where you got to have a little bit of problem solving skills. Okay, let's look at the last example for today's lesson. Hey, good surprise. Looks like we don't have another problem for today's lesson. So that is it on 311 day 1 related rates. Read through this kind of steps for solving related rates. Once you get used to the process, you won't necessarily be following an 11-step process. This is just for initial purposes. Once you get to it though, and you get some practice in, you're likely going to be right on. So, okay guys, we'll see you in the next video.